Hello, physics class. We're going to finish up our week of magnetism with a look at magnetic force. There is one formula, and we leapt over a lot of information several chapters on electrical forces and electrical charges. And so I've cut about 2/3 of this section out. It's just there's too much background information that we don't have. But the important thing is that we can progress forward and get a little bit of an understanding about how some of the one formula we'll look at kind of relates electric charge to force and velocity. Those three things are related. So here's the goal. Given the force on a charge in a magnetic field, determine the strength of the magnetic field. Um, hmm. You're going to need to know more than that. I'm sorry, I'm thinking this out. You're going to need to know more than the force on a charge in a magnetic field. You're also going to need to know the magnitude of the charge and the velocity of the charge. There we go. Sorry for this long, awkward pause, but I just want to be honest with you guys. Okay, so if you're given the force on a charge in a magnetic field, the magnitude of a charge, of an electronic charge, is passing through that magnetic field, and the velocity of the charge determine the strength of the magnetic field. Okay, so section 1, which is the only section, charged particles in a magnetic field. In a magnetic field, charged particles experience a magnetic force. Here's what you need to know. Here's what you should know, but we're going to ignore some of the geometry of this thing. So in a magnetic field, these three things are always acting perpendicular to each other. There's the magnetic field has a direction. The sound you hear in the background is my wife making coffee, grinding coffee beans. Bless her soul. Again, you've got a magnetic field, and that's a vector, so it has a velocity. It has a magnitude and a direction. So that direction is important. If perpendicular to that direction, you have a charged particle that is moving through that magnetic field perpendicular to that. That's one action, and that generates a force that is also perpendicular to both of those things. So think of your x, y, and z grids that you see, and there's another right-hand rule where you stick your thumb in one direction and your index finger in another, like you're pointing a gun, and then you stick your longest finger kind of perpendicular to your index finger and your thumb. That's another rule that if you're taking more physics in college or later next year in high school, you may get into this other right-hand magnetic rule. But anyway, we're going to just assume that everything's operating with the perfect geometries, and we're not going to bother with any other assumptions. So if you have a charged particle, some electron or some proton that's moving through a magnetic field, it will experience a magnetic force. And you know that forces can be measured in newtons. A charge moving through a magnetic field experiences a force. So all these terms are new except for force, which is Newton, some good old familiar Newton. Here's the formula you need to know. This is hairy looking, but because of all the different letters, but it's not that complicated. B equals F submagnetic, the magnetic force, divided by Q times V. So here's what that means. B, as you remember, or hope you remember, is the magnetic field. And the magnetic field equals the F submagnetic, which is the magnetic force on a charged particle, divided by the magnitude of the charge, that's Q. So Q means the magnitude of the charge times the speed of the charge. Okay, every single one of these terms is represented by multiple letters, unfortunately. So B represents the strength of the magnetic field and is measured in Teslas, or T. The magnitude of the electric charge, that's Q, is measured in coulombs, which is C. Oh my gosh, this sounds horrible. This is a lot of information to be coming at you solely from a video here. But anyway, we'll hold our hands together and we'll see how we can do. And then the speed of a charge, of the electric charge, V, that's velocity, is measured in meters per second. Okay, so that looks familiar too. We know about that. So let's take this formula for a test drive, shall we? Yes, we shall. Oh, no, we haven't done this. The magnetic force, F sub magnetic, is measured in newtons, N. Now we're ready for a sample problem. So let's say we have some lonely proton with a charge of 1.6 times 10 to the negative 19th coulombs moving east that experiences a force of 8.8 times 10 to the negative 19th newtons upward due to the Earth's magnetic field. I'm going to pause here. That proton with that charge, 1.6 times 10 to the negative 19th coulombs, that is the standard charge for a proton. So all protons have that charge. You don't need to remember that number, but you just need to know it. An electron will have negative 1.6 times 10 to the negative 19th coulomb charge. I'm going to give you a little homework assignment that will consist of 3 problems, and like in this sample problem, I'll remind you of the charge of the proton or the electron that's moving through here. So we're just going to calculate the magnetic force on a single proton or a single neutron, or given the magnetic force, we'll calculate the strength of the magnetic field, something like that. Okay, so at this location, the Earth's magnetic field has a magnitude of 5.5 times 10 to the negative fifths Teslas to the north. Find the speed of the particle. Okay, so let me refresh your memory. Here's what we've been given. The electric charge, Q, is 1.6 times 10 to the 19th coulombs. The strength of the magnetic field is 5.5 times 10 to the negative fifth Teslas. Magnetic force is 8.8 times 10 to the negative 19th newtons. And I've given you enough information now, except that I should probably remind you what the formula is. So there's our problem again. Here's the formula that we're going to start with. That's the formula that we've been given. The strength of the magnetic field is the magnetic force divided by the electric charge times velocity, okay, of that charge. So I'm going to just do some algebra here on this thing. So you can see my mouse, I believe. So on both sides, I'm going to multiply by V, and I'm going to divide by B, and I'm rewriting this equation this way. It's the same equation. I've just multiplied by V, divided by B, and here it is. And I'm doing that because we need to find the speed of the particle. And so now if I can just put in my numbers, which I'm going to do right here and right now, then I will get directly the velocity, the speed of the particle. So magnetic force is 8.8 times 10 to the negative 19th newtons, and that divided by the electric charge, 1.6 times 10 to the negative 19th coulombs, times 5.5 times 10 to the negative fifth Teslas. And if I do that calculation, I get a velocity of 1 times 10 to the fifth meters per second, which is like 220,000 miles an hour. So this proton is cooking. Okay, I know that this is complicated stuff to be presented to you in the way that it's being presented, but I know that you can do this. I'm going to give you 3 homework assignment problems that look very similar to this. They all use this formula here. Sometimes you're going to solve for different variables, and so it's just a simple algebra manipulation. But if you have questions, certainly email me. We can talk it out. Okay, we can even FaceTime if we need to, or Zoom meet if we need to be able to kind of hunt down the solution to the problem you're looking for. Okay, So that's all I've got for you today. Go be awesome.